What's up, my stat stars? Michael Princhak here, ready to talk to you about random variables. Random variables for some kids can be very difficult to understand because it's a combination of probability and understanding possible different outcomes and how to calculate the probabilities of those outcomes, which all together kind of makes it a little bit tricky. So let's dive into the top 5 things that you need to know when it comes to discrete random variables. But first, we should probably remind you what a random variable is. So if the outcome of a chance process is a numerical value, then that outcome X can be described with a random variable. Now we typically use capital letters to represent random variables like X, Y, Z, W, T, whatever you want to use. But keep in mind that the most important idea of the definition of a random variable is that the outcomes must be numerical. So if you have a situation where you don't know exactly what's going to happen, the outcomes are what we say random, but if those outcomes are numerical values, then those numerical outcomes can be described with what we call a random variable. Now, there are 2 different types of random variables. The one we're going to focus on this video is a discrete random variable. A discrete random variable is when those numerical outcomes are distinct and listable. Basically, they're finite. Whereas a continuous random variable, the second type of random variable, is the outcomes, well, they're continuous. They could take on literally any value that's possibly out there. Now, some values might be more likely than others, and some values might be really unlikely, but the point is with the continuous random variable, there's just far too many infinite outcomes for us to even think about. Now, in this video, we're going to focus on discrete random variables, but a lot of the same exact concepts apply. So when you do learn about random variables in Unit 5, you'll be ready for the continuous random variables as well. Now, the first thing that you have to know when it comes to discrete random variables is how to create or how to read a probability distribution. Now, a probability distribution for a random variable X is simply a list of all of the possible outcomes, and underneath or next to each of those outcomes is the probability of those outcomes. Now, sometimes this table or graph could be given to you, which is probably awesome, best case scenario, but other times you're going to be asked to build it on your own. Here's an example where that graph is given to you. So we have random variable G, how many goals Lily scores in a soccer game. So across the top here, we see the outcomes 0, 1, 2, 3, and 4. And underneath them, we see the individual probabilities. So we have capital G, the overall random variable for how many goals Lily could score. And then little g would be like each individual outcome. So 0, 1, 2, 3, 4 be like our little g's. So the probability that the capital random variable, how many goals she scores, equals the little outcome or the individual outcome of 0, in this case is 55%. And then we also see the probability of 1, 2, 3, and 4. Now, a couple key things to recognize that all the probabilities in a discrete probability distribution have to add up to 1. If they don't, something's not right, so you might want to fix it. But once you have one of these probability distributions, it's really easy to ask you some basic questions. What's the probability she scores 3 goals? 2%. What's the probability she scores 1 goal? 35%. I could even ask questions like, what's the probability she scores at least 1 goal? Now, there you got to remember, okay, at least 1 means 1 or 2 or 3 or 4, 1 or greater. She can't score 5. It's not even listed in the table. So 2 ways that we could find the probability of at least 1. We could add the probabilities of 1, 2, 3, or 4 together, and we get 45%. Or we could just think about what we don't want. The opposite of at least 1 is none. So if we take away the probability of no goals, which is 55%, 1 minus 0.55 is the remaining 0.45, which would be everything else, which is at least 1. So that question about find the probability of at least 1 is a very common question on the AP exam. And you can find the probability by, again, doing what you want, 1 or 2 or 3 or 4. But sometimes it's a little bit quicker to do if you just get rid of none or 0, which in this case is just getting rid of that 55% from 1, and we get 45%. But again, this is a probability distribution, nice and simple, especially when it's given to you. Now, in some cases, you're going to be given information and asked to build your own probability distribution based on a scenario. So let's look at one now. Pepper the Pig is entered into 2 pig races. Now, the probability Pepper the Pig wins the first race she enters is 60%, so we automatically know she's got a 40% to lose that first race. Now, here comes some conditional probabilities. If Pepper wins the first race, so that has to happen first, the probability she wins the second race is 85%. So maybe the confidence of that first win gave Pepper some confidence. Now she's got an 85% chance to win the second race. So that would be a 15% chance to lose the second race. However, if she loses the first race, Again, conditional because she's got to lose that first race first. Then the probability she wins the second race is 25%. She lost the first. She's kind of upset, so now she has a less chance to win that last race. And then again, the probability she loses that race would be 75%. So let W be the random variable for how many wins Pepper gets. Now, the first we got to figure out is, well, how many wins can she get? Well, she could win both races. That would be 2 wins. She could lose both races. That would be 0 wins. Or she could win one of them. But winning one of them has 2 different combinations. Lose the first, win the second. That's a total of 1 win. Or win the first, lose the second. That's also a total of 1 win. So how do we calculate those probabilities? Well, because we have some conditional probabilities in this problem, a tree diagram is going to help tremendously. So the first branch of the tree is that she wins the first race, which we know is 60%, and then she wins the second one, which we knew was 85% on the condition she won the first. So that would be the probability following that branch that she gets 2 wins. Next, we could continue on with she wins the first race, 60%, but she loses the second, which would be that other 15% from the 85 that she wins. So that branch, 0.6 times 0.15, would be winning 1 race with the first, not the second. Then we got the bottom branches losing the first race, 40% chance probability. And then from there, she could win the second race, 25% chance to win that second race. So that ending branch would still lead to her winning 1 race. Lose the first, win the second. And then the final branch at the very, very, very bottom, lose the first, 40%, lose the second, 75%, and that would end with 0 wins. So then we could put all this into a table. So again, we have across the top the outcomes for W, how many wins Pepper gets, 0, 1, or 2. And then we could include the probabilities. So to find the probability of 2 wins, she's got to win the first, win the second, 0.6 times 0.85. To get 0 wins, she's got to lose both. That'd be 0.4 times 0.75. And then the other options, well, there's actually 2 of them because she could win one or win the other, but that, adding those options together because both of them result in winning 1 race. So that would be the 0.6 and then the 0.15, won the first, not the second. Or, so we need a plus sign here, lose the first, 0.4, then win the second, 0.25. That would also lead to her winning 1 race. So at the end, we do the math. We get our final calculations for our 3 probabilities for 0 wins, 1 win, or 2 wins. So there you go. We just built a probability distribution based on some conditional information given to us. And now we have this discrete random variable, how many wins Pepper gets, and we have the probabilities for each. Overall, not too bad, but a really good problem because it incorporates that basic probability that we've already learned into random variables. All right, the second most important thing you need to know about discrete random variables is how to calculate the mean of a discrete random variable. Well, here is the formula to calculate the mean. It's pretty simple. Let's just talk about it real quick. First, we use the symbol mu for the mean, and then we have the little subscript x. That's just saying, hey, the mean of the random variable x that we're talking about in a specific problem. Now, formula looks a little bit funky, but it's actually really, really easy to do. You simply take each outcome multiplied by the probability of that outcome, and then you do that for all of your outcomes, and then you add them all together. So that Greek letter there, that Greek letter looks like an E, it's called sigma. That means sum them all up. So again, each outcome times its probability, plus next outcome times its probability, and so forth until we've summed up all of the outcomes times their probabilities. Overall, not too bad. Now, understanding what it represents is equally important to being able to find it. So the mean is also known as an expected value. It's what we expect to happen in the long run, or it's the average in the long run. So the mean, or the expected value, is the average for the random variable if it were to be repeated many, many, many times. So if we were to repeat this random variable x, we don't know what's going to happen, but repeat it over and over and over and over again and kind of keep track of what happens after an end of each chance process or after each occurrence of the random variable, it would be the average of all of those in the long run. Now, it's not saying, hey, well, let's just do it 5 times and find the mean. No, let's not just do it 10 times and find the mean. No, the mean of a random variable is what we expect to happen in the long run after many, 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 many trials of this random variable, which is why we use that symbol mu to represent the mean in the long run, the true mean of the random variable or the average or the expected variable in the long run. All right, let's look at an example of how we can actually do this for a specific problem. Let's go back to random variable G, how many goals Lily scores in a game. So if we take each outcome times its probability and add them all together, we get a final result of 0.59. Now, what does that 0.59 mean? That means in the long run, if Lily were to play many soccer games, and every time she plays a soccer game, Lily records in her journal, hey, I scored 1 goal, 2 goals, 0 goals. In the long run, after many games, she expects to score an average of 0.59 goals per game. Now you might say, well, she can't do that, and you can either score 0 and 1. You can't possibly score 0.59 goals. I know, it's an average in the long run. A great example I like to use is LeBron James. His career average is 27.2 points per game. He's never going to score 27.2 points per game. It's an average of the many games that he scores. So in tonight's Lakers game, we expect him to score 27.2 points. Obviously, it could be more or less. So in a minute, we're going to talk about standard deviation, but it's an expectation. It's an average in the long run. Now, the third thing you need to be able to do is calculate that standard deviation, because we do expect the mean to occur in the long run, but it could be a little bit more, it could be a little bit less. So here is the formula for the standard deviation, sigma of that random variable x. Now, what we're going to do here is we're going to take the difference between each outcome and the mean, so we can do it to find the mean first, square that difference, multiply by its probability, and then do that for every single outcome. Outcome minus mean, squared times probability, repeat. Add all that together. Now, that inside part is called the variance. Then we square root all of that variance to get what we call the standard deviation. So the variance is the inside part, or the standard deviation squared, because if you square the square root, it goes away and you just get that inside portion. That is known as the variance, whereas once you square root it all, you get your standard deviation. Now, you can use this formula, but it's definitely a little bit trickier to use, whereas the mean is pretty fast and not too bad to do. Calculating standard deviation by hand is not very fun. So typically what we're going to do is we're going to use our calculator to calculate the standard deviation of a discrete random variable. Let me walk you through this very simple process. First, you're going to hit the stat button and go to edit, and you're going to edit into your lists. Now, in list 1, you're going to put your outcomes. So let's talk about Lily and her goals per game. So in list 1, we're going to put the outcomes 0, 1, 2, 3, 4. And then next to that, in list 2, we're going to put the individual probabilities of each of those outcomes. Then we're going to quit out of there. Then we're going to hit stat again, slide over to the middle, calc, and select one variable, stats. Now, here's something that's really important. Where it says lists, we're going to put L1. That's where our outcomes were. But now we need to incorporate the frequencies, or the probabilities of those outcomes, which is list 2. So where it says frequency list, you need to hit L2. Then hit calculate, and you will get the standard deviation, sigma, right there kind of in the middle. In this case, 0.789. Now, notice what you also get at the very top is the mean. So to be honest, you don't even need the formula to find the mean of a discrete random variable, because the calculator could do both the mean and the standard deviation for you. Just be careful, because the calculator doesn't call the mean mu, it uses x bar. You need to know that you're talking about a random variable mean, so that's a long-term, long run, over and over, repeat mean. So you need to know to label that with the mu, but the standard deviation is probably labeled as a sigma. So at the end of the day, all you got to be able to do is find the mean and standard deviation, hopefully with your calculator, or by hand if you want to use the formulas, knock your socks off. But it's overall not too bad. Just make sure that you really know that the mean represents the average that we expect that random variable in the long run. But of course, that expectation could be a little bit more or a little bit less, and that's why it has a standard deviation with it as well. Now, the fourth thing we need to be able to do with discrete random variables is transform them. Now, what do I mean when I say transform a random variable? Here we're talking about 3 different situations: adding or subtracting a constant to all of our outcomes, multiplying a constant by all of our outcomes, or you might say, well, what about dividing? Well, remember, division is the same thing as multiplying by the reciprocal, so division can also be looked at as multiplication. And then we also have converting from one unit to another unit. So that's what would take place as well. Like maybe we're going to go from inches to feet, or miles to inches, or something like that, and we're just converting. So the 3 different ways that you can transform are those. Now, how does transforming the random variable affect your mean and your standard deviation? Because that's usually a typical big question on the AP exam. Well, first, adding or subtracting a constant to all of your outcomes will only affect the mean. So if you're adding 9 to all of your values, well then the mean is going to go up 9. But the standard deviation will not be affected by addition. Standard deviation will stay the same if you're adding or subtracting a mean, if you're adding or subtracting a constant to all of your data. However, multiplying a constant to all of your data will multiply the mean and the standard deviation. So both mean and standard deviation are affected by the multiplication of a constant to your data. So here's a really quick example that you're obviously going to typically see on a unit test or an AP exam dealing with this concept. So we have a random variable x. They tell you the mean is 16, the standard deviation is 3. And then they say, okay, we have a new random variable y that's defined as 5x plus 7. So you're going to take x, multiply by 5, and add 7. What is the new mean? What is the new standard deviation? Well, remember, multiplication and addition both affect mean. So we're going to take the old mean of 16, it's going to get multiplied by that 5, and we're going to add that 7 to get a new mean of 87 for the random variable y. But for the standard deviation, we do not add the 7 because remember, adding a constant does not affect standard deviation. So it will multiply though. So we have the 3, that was our old standard deviation, times the 5, and we get 15, and that's it. No adding or subtracting to that standard deviation. All right. The other thing that we could do with transforming a random variable is converting from one unit to another. So let's just say that the random variable x that has a mean of 16, a standard deviation of 3, is measured in kilograms, and we want to convert it to pounds. Well, first we need the unit conversion factor. That is that 1 kilogram equals 2.2 pounds. Then we just have to multiply, hopefully you guys might know that from chemistry class, to convert our units, that's again currently in kilograms, to pounds. And if we're multiplying, multiplication affects both mean and standard deviation. So our new mean is going to be taking that 16 that's in kilograms and multiplying it by 2.2, because 2.2 pounds for each one of those kilograms gives us a new mean of 35.2 pounds. It's the same mean, just in a different unit. And our standard deviation of 3 is also going to be multiplied by 2.2. Again, all I'm doing is converting it to pounds, and I get 6.6 pounds. So pretty simple. Just understand that addition or subtraction of a constant does not affect standard deviation whatsoever. Multiplication, however, does. All right, and the very last topic for discrete random variables is combining random variables. And this is probably the most important because it's the one that most kids don't understand or forget about and cause them to get a lot of problems wrong. Now, what do I mean when I say combining random variables? Well, two things, either combining two or more random variables together or repeating a single random variable multiple times. Now here we're not talking about just converting or adding or subtracting constants. Here we're actually doing multiple random variables together, either multiple random variables all kind of combined or a single random variable repeated multiple times. So the process is a little bit different here. But here's the basic rules. Means can be added to find a total, or means can be subtracted to find a difference. That's pretty simple. However, standard deviations can never, ever, ever be combined in any way. You can only combine variance. Now remember, variance is just standard deviation squared. So if you know your standard deviation, all you gotta do is put a little square on it and boom, you have variance, and you are allowed to combine variance. But here's the last little bit of information to look at an example. Variance always adds even if you're looking at a difference. So even if we're looking at the difference between two random variables, the fact is we're still putting those two random variables together, which means the variance always builds up, never diminishes, never subtracts. All right, so let's look at an example here. So we have two random variables, x and y. We're given the mean and the standard deviation for x. We're given the mean and the standard deviation for y. Nice and simple. Now let's talk about adding them together. So we're going to combine them together and get a total. So we're going to take x plus y to get a total t. Now, what is the mean and the standard deviation for the total? Well, first off, means they're allowed to add. Take the 15 from x, take the 8 from y, add them together, we get 12. Very, very simple for our mean. But keep in mind, standard deviations cannot be added or subtracted, but we are allowed to combine variances. So the variance for x is simply the standard deviation for x, 2.5 squared. Now, you don't even have to find it. Like, I don't want you to tell me what 2.5 squared is. Just put that little square on it and you just instantly change standard deviation to variance. Then we're going to add the variance from y, that's 1.3 squared. 1.3 is the standard deviation for y. Squaring it instantly turns into variance. We are allowed to add that variance together. But now we need to get all of that variance back to a standard deviation. So we're going to put a giant square root around all that variance, because once you have variance, take the square root of it and you get standard deviation. So it's a little bit of a tricky procedure, but hopefully it's not too bad. Again, just taking the 2.5 squared variance for x plus the 1.3 squared variance for y, add it together, square root around that total, and we get 2.818. Now in this next example, we're going to look at the difference between x and y. All right, well, as I mentioned, my first rule, you are allowed to subtract means. So what is the difference between the x and y? Well, I expect a difference of 4. X is supposed to be 12, y is supposed to be 8, so the difference is going to be 4. That's so easy. But what about the standard deviation? Well, first, I'm not allowed to even work with standard deviation. I have to work with variance. And my third rule was that variance always builds even when you're looking at the difference. So I'm going to take that 2.5 squared, I'm going to take that 1.3 squared, that's the variance for x, the variance for y, and I'm still going to add them together even though I'm looking at the difference. The fact remains I'm still bringing these two random variables together, so there's going to be more variance. Take that giant square root around all that variance to get back to standard deviation, and I get the same standard deviation I had when I added them, 2.818. All right, final example, let's talk about repeating a random variable. So let's say that we're going to have k. K is a random variable of repeating random variable x 7 times. So we're going to do random variable x, we're going to do it again, 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 and I think that was 7. All right, so what is the mean? Well, every time you have random variable x, you expect 12. So it's 12 plus 12 plus 12 plus 12 plus 12 plus 12 plus 12. Now, obviously, we could speed up that addition. It's much faster to speed up addition with multiplication. But please note here, I'm not multiplying to convert or multiplying by a constant. I'm multiplying to speed up addition. It's a different use of multiplication. So we have multiplication for conversion, and we also have multiplication for speeding up addition. That's exactly what I'm going to do here. 12 times 7 to get 84 is my mean. Next up, for the standard deviation, once again, I'm not allowed to combine standard deviation. I'm only allowed to combine variance. So I have 2.5 squared. That's the variance for x. But I have to repeat that 7 times. So it's 2.5 squared plus 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 2.5 squared. And once again, I can use multiplication to make that addition faster. So I'm going to take that 2.5 squared, that's my variance for x, but I got 7 variances of that repeated random variable x. So I could do the 2.5 squared times 7 all inside of the square root. But again, why am I putting it inside the square root? Because I have to square root my variance to get back to a final answer for standard deviation. So again, it's basically saying, hey, I got 7 random variables. I got the variance, the variance, the variance, the variance, the variance, variance, the variance, 7 variances, 2.5 squared times 7, square root it all to change all that variation back to standard deviation, and I get my final answer, 6.614. All right, that's it for the top 5 things you need to know about random variables, focusing on discrete random variables. Now, the cool thing is all of these rules apply to continuous random variables, as you're going to learn about in Unit 5. The only thing you cannot do is build a table for a continuous random variable, because remember, the definition is that the outcomes are infinite, so how could you make a list of infinite possibilities? Well, we're actually going to talk about that in Unit 5. But the rules for transforming, the rules for combining, all that fun stuff is still the same. All right, that's it for discrete random variables. Hopefully it made a lot of sense, and check my other videos out if you need more help.